Okay, good afternoon, dear students. Please, you can just type for me to say good afternoon so that we can start the class. Like I mentioned, when I just come in, I log in, then I'll start teaching, so we don't have time to start waiting. So please, you can just for those who didn't write the test, Mr. Moyo has uploaded the test. Okay, that's good. So we can then start the class because we don't have time to start wasting. Okay, like we ended on for the area which is of the region which is bounded between two regions. So we are going to conclude with the volume, anything to do with the volume. So now, one thing that we should remember is that the same calculus, we can also use it to find the volume of an unknown vessel. So you have this vessel that you can't manage to compute its volume using the basics that you learned at secondary school, whichever level. So what you can do is you can find the volume of such unknown vessels using calculus. We call it the volume by slicing and rotation about an axis. So we compute this by either rotating the object and then you're able to determine the volume of rotation or at around 60 degrees angle. Now, basically, as we'll be going through this way, I'll be skipping some of the concepts because you're able to read some of the notes and then you just um, after going through, then you'll be able to follow. Okay, now, so let's look at some concepts that involves the volume of the space. No, let's look at definition number 13. So under definition number 13 of from our notes, lecture notes, I know there are other statements that has been written before the definition, but we are interested for now. We are just looking at the analytic part of these concepts. So this definition, please bear me as a witness. I'm not going to write the whole of this on the board. I'll just go read through it. Then when I start now computing the examples, then we are going to I'll link you to the board. So we are saying let me just pull it. Okay. So we are saying if we have a solid, this solid that we can't compute its volume properly. So we are saying let S be a solid that lies between x equal to A and x equal to B. So you have this object, for example, you have this object like a stone which is sitting there, and then you try to sketch an x or y plane curve and you put the coordinates. Then now this solid, it lies between the point x equal to A and x equal to B. Now, if the cross-section area of S in the plane PX, this plane is an x or y plane, through x and perpendicular to the x-axis is AX. So what we are saying is, if you are able to find the area of this solid, remember, we started by calculating the area of a region that is bounded between curves, or that is below the curve and the x-axis. So what we are saying is, the cross-section area is like the base area of this given object. Now, if the area of this given object is AX, which is a function of x, where A is a continuous function. So what we are saying is that, like the way we started with curves, if you are given this curve, and then this is the area of the given object S, then the volume of that given object is given by, which is the Vs, which is equal to the integral of from the point A to the point B of the area of that given, the cross-section area of that solid object S with respect to X. So then what you have done, you have found the volume of the given region in that format. Now let's look at what we call the volume of rotation, solid of rotation. Now we have two different methods that we'll be using to to compute the volume of a solid object with the cross section area being AX. Now, the first one, we call it which we are calling the solids of revolution, the disk method. So we are going to look at the disk method. Then from the disk method, we are also going to look at some other properties that involves the volume of rotation. Now, so let's start with the disk method. However, now so I'll pull through my notes. So let's look at the first part of our notes, which is the solids of revolution, the disk method, which we are calling the disk method. So we are only going to look at this type of method for evaluating the volume of revolution of a given object. Now, the first thing that you need to understand is a solid of revolution. So what is a solid of revolution? So we are saying a solid of revolution is a solid generated by rotating a plane region about an axis in its plane. So what happens is this. If you rotate a plane region, you try to rotate it, what it will form something like a solid. Like I mentioned to say, for example, if you are given, if you look at the way the vehicles move, and then the wheels starts rotating, or let me say the fan which is found at the engine, there is this fan which is found at the engine, or the normal fans that we have at home. Let me just say the household fans. The household fans has this propeller. Now, when that starts rotating, then I tell you which piece is this one. Or if we label those pieces, if it has 3 pieces, piece 1, piece 2, piece 3. Now, if it starts rotating, what you see is not those pieces for the fan. What you see is something that is just solid. Now, a portion of a curve y is equal to f of x between the ordinates x equal to a and x equal to b is rotated about the x-axis through 360 degrees. So when this happens, when you rotate this solid, when you rotate this object which is in the plane, you rotate it through 360 degrees. So in the process of rotating it, what you see is the figure which is given below. Let me just show you. So it's this figure which is given below. So this is the solid of revolution about the x-axis. Maybe at this stage, at this point, let me show you why at the end of it all, what you see is some kind of like a solid. Let me just show you something on the board. Okay, so what we are saying here is this. So if you pick a wire, you have an x or y plane. So in the x or y plane, so let's just say this is the origin. Now you have A, and again you have B. So you pick a straight wire. Let's give an example of a straight wire, and then you fold it. You form something like maybe how can I put it? Okay, let's just for argument's sake, we form something like this, and then this piece comes and end here. We also form something like that, and then this piece ends there. So now the distance from here to here is b minus a, so from point A to point B. Now, what will happen is, if you rotate this, so if you rotate this wire, so if you rotate it, what you're going to see is something of this nature. What you're going to see is something of that nature. Okay, so you have something that to be like that we are calling a solid of revolution. Okay, so we are going to have a solid of revolution. So we have this point A. Okay, so we have that radius. Then we also have the distance from there up to there. So when you rotate it, when you rotate this object, what you're going to see, it will be rotating as being a solid of. So when you rotate it 360 degrees, what you see is something so solid like this one. You're not going to see like a simple wire. So now, when you have such a situation, this x-axis is an axis, is an axis of symmetry, and any cross section perpendicular to the axis will be a circle. So this line, this line is in the middle of this object. Now, when you rotate it, so now any cross section that you form, when you rotate it, you are going to form something like a circle. Okay, it will form something like a circle of radius, the length, that circle be of radius, the length from this point to from the x-axis to the top or from the x-axis to the bottom. Maybe if I put this to be like point A, this to be like point B. So the radius will be just the length from this point up to point A. Now, you can either form a circle or you can form something, a solid, which is a cylinder, whichever kind. Now, to find the volume of that solid that you formed, remember, you had a wire and then you folded it. You formed something like a ring, you put it there, then you rotate it. What you formed is a circle, isn't it? Now, to find the area, uh, to find the area in general, to find the volume of the, what we say, the volume of rotation. Now, if you look at the formulas for the area of a circle, the area, remember, the area, let's just start with the area. So it forms a cross section, which is a circle or which is a cylinder. Now, the area of a circle, that when we rotate this, it will form this circle of radius from this point to that point. Then the area of this circle, okay? Now, the question, maybe before I go, so the area of the circle that is formed by rotating this object is pi r squared, isn't it? Where, let me just use the word radius, pi times the radius, the square of a radius. Now, the question is, what is our radius? Now, our radius is the length from point B up to where, and this is, so this is a curve. Remember, by the way, this is a curve. This side it continues going, this side it continues going. But because we want to find the volume of the map, what is this curve? This curve is the curve y equal to f of x. Isn't it? So this curve is the curve y equal to f of x. So now if I ask, what is this point? You can say this point is f of b. What of this point? It's f of something. This point is f of a. There's another point. So in general, this point is a point f of x. Every point along this curve is a point f of x. Now, so it means the distance from here to there, we are going to get f of x. So where there is this radius, we put pi times f of x squared. So that is what you're going to have. Now, the issue here now, after we have simplified this, now what is the volume of the portion of the curve? Now, if this is our curve, the general area of this curve is this. Now, what is the volume of the portion of this portion? Instead of us going to this side and that side, instead, we just want to find the volume of rotation of this portion of this curve, of the portion of this curve. This is the only part that we want to compute its volume. So then we are now going to have, this is the one now you've seen. So from this concept, that's when now we generated the area of rotation. So from your definition, this is definition number 15. This definition says that part 1, if a portion of a curve, if a portion of a curve y equal to f of x, y equal to f of x is rotated, is you rotate this portion of the curve about the x-axis, about you rotate this portion of the curve about the x-axis. Now, so you decide to rotate this portion of the curve about the x-axis, then the volume of rotation, of this curve y equal to f of x is given by, so from, let me just say, from x equal to a to x equal to b is equal to, so volume of rotation will be equal to the integral from a to b times the volume of rotation. So this, times the integral from a to b of the area, which is pi times f of x squared dx, of which you can simplify this to the pi. Since pi is a constant, it's just pi times the integral from a to b of f of the square of f of x dx. So this is a situation like graphically, this is a situation like the one that I've given here. An example to this is the graph that I've sketched here. So if we want to calculate the volume of rotation of a portion of this function y equal to f of x, so if we want to calculate the volume of rotation of the portion of this function y is equal to f of x around this region, what we get is this. Let me explain something here. So this is what happens. Let me sketch it. So you have this function. So you have this function that will be given. So you have this function that you have been given. So maybe let's say this function is from point A. From point A, this is y, this is x, to point B. So this function maybe comes like that. It goes like that, like the square root of maybe 2 or the whichever square root of something. So this function comes like that. It can touch anywhere. Maybe it comes like that. Then it goes down. Okay. Now, what we want is to find the volume of rotation from point A to point B. So our function continues going. So this is the function y equal to f of x. Then now, so then we decide to hold this function from the point A, from this point A. Then we hold it somewhere there. Then we try now to rotate. So when we hold it somewhere, so we are going to form, so when we rotate this piece up, the distance from this point to that point up to where it reached down here to be the same, and also somewhere this side. So in short, when you rotate this, what you're going to get is a solid of revolution. So when you rotate it, so we are going to have something like that. So then you have something like that. Then you have something like that. So when you rotate it, then you should be able to find the volume of rotation. This is just the one which is down is just a reflection of the original function. So we decide to cut it and rotate a portion of this function. So what we get is this is equal to V, the volume of rotation of this portion of the curve, which is rotated 360 degrees, is equal to pi times the square root from a to b of f of x, uh, then pi times the integral from a to b of the square of f of x dx. Okay, now the other thing is now what happens. Let's go to number 2. Part 2, similarly, if a portion, part 2, it says, uh, so part 2 says, if a portion of a curve y equal to f of x is rotated, so if a portion of a curve y equal to f of x is rotated about the y-axis, here now, the point of rotation is on the y-axis. The point of rotation is on the y-axis. Then the volume of rotation of y equal to f of x from y equal to c to y equal to d is given by, so now here now, this is now given by the integral from a to b. So let me do this. So this is now given by the volume of rotation along the y-axis. This is equal to the integral. This is the integral of the cross-section area with respect to y from a to b of dy. Now, our cross-section area in this scenario now becomes the integral from a to b pi, then f of y squared dy. Okay, which we can factor out the pi. We can have a to b, then f of x squared dy. And in this case now, your cylinder will look like this one. So your cylinder then now, your volume of rotation of this portion, which lies between those points, in this scenario now, we are going to have a situation like this. So you have this, and then you have maybe a function, maybe which comes like that, maybe a quadratic function, which goes up this side. Maybe it goes, maybe you have something like that, which is a shift. Now, you want to calculate the area, the volume of rotation from point C up to point D only. So you want to rotate this portion of the graph of the curve y equal to f of x. So what you need to do is to make a point there, and then we can get rid of this part. Then we have something like that. We have like something like okay, so we have something like that. Then we can have something like that. Then we have something like that. Sorry. Okay, so now we have that distance. We also have that radius. Then we have a C there. So when we rotate this counterclockwise or clockwise, so you have this rotation. You rotate this piece like this, it starts rotating. What you're going to see is something as solid like this one. Okay, now let's look at some examples. So having said all this, let's look at some examples. I think there's only one example that I'm going to solve using both methods, which is your example number 16. So once we are done with this example, we can call it the end of, sorry. So we are going to say this is the end of the class because that is the only part that requires much of our attention. Now, so this example number 16, let's look at the example number 16. Example number 16. So let's look at example number 16 says the portion of a curve. So this is example 16. It says the portion. So this example says the portion of a curve. We have a curve y equal to x squared. So the portion of a curve y equal to x squared between, so this portion of a curve between x equal to, so the portion of a curve between x equal to 1 and x equal to 2, okay, is rotated through 300, and so you rotated through what? 360 degrees. Then the first question is about 1, the x axis, 2, the y axis. Now, the question is find its volume. Find its volume. Find the volume of this portion with respect to the axis of revolution. So we are supposed to find the volume of this portion with respect the volume of rotation of this. Find its volume of rotation. So we are supposed to find the volume of rotation of this portion, which is bounded by the curve x y equal to x squared, x equal to 1 and x equal to 2, with respect to the x-axis and also with respect to the y-axis. Now, you can't start solving without you first sketching the graph. Let's sketch the graph. If you look at y is equal to x squared, it's graphically we have something like this. I hope you're able to see what I'm sketching. We have y, so we have x. Now x equal to 1. We also have x equal to. So it is from x equal to 1 let's do this. So along the x-axis, so the line of symmetry here is the x-axis. So y is equal to x squared. If you look at y is equal to x squared, this graph looks like this. This is how this graph looks like. So this graph is y equal to x squared. Then now, what is happening is, you can't see the camera. Okay, I hope you are now able to see. There's a reflection. Okay, all right, so now after you sketch this curve, you realize that this curve let me sketch it from the other side. Okay, let's look at the solution. So we have this curve. This curve is the curve y equal to x squared. Okay, that's how it looks like. So we have the y-axis, we also have the x-axis. Now, what they are asking us is to find the volume of revolution from what point to what point. So this volume of revolution so is from 1 to 2. Okay, so this is 1, 2. So we need to have something down, down. So which means if at all I say we reflect this, this will look like this. So what they want us is to find the volume of revolution to that region. So the portion that we are talking about is this portion. Okay, so just for this portion, so that is the portion they are talking about, that they want us to find the volume of revolution. Now, how can we compute that? This is a situation where the, this rotation is with respect to the x-axis. This is a situation where the rotation is with respect to the x-axis. Then, if this is the case, then volume of revolution with respect to the x-axis of this function is equal to the integral. Now, from A to B is from 1 to 2. So from 1 to 2, so it is equal to pi times the integral from 1 to 2 of, what is our function? Of the function. Now, the square of the function. Now, what is our function? We can just say of y squared. Our function is y. So then this is equal to pi times the integral from 1 to 2 of x squared dx. Okay, so now this is just equal to pi times the integral from 1 to 2 x power 4 dx, which is going to give us, and this is going to give us x power 5 over 5 from 1 to 2. Now, using the fundamental theorem of calculus, this is 2 power 5 over 5 minus 1 power 5 over 5, which will give us 32 over 5 minus 1 over 5. At the end of it all, we are going to have 31 over 5. Now, volume, the unit for volume is units cubed. Part 2 with respect to the y-axis. So you have to be careful when you're computing this volume with respect to the y-axis. So before you do that, you are first supposed to change the variable of integration. But either way, the first thing is, let's first try to sketch it. Again, I will sketch it again. So we have um, the x or y plane. Okay, so we have the x or y plane, and the graph to this curve is this curve goes like that, and then it goes like that. Okay, so this other one, so this is our answer. This other one is number 2 with respect to the y-axis. So this is our curve. This curve is the curve y equal to x squared. Now, this is where now it becomes challenging. So you have to make sure that you recognize the question. You have to read the question and understand it. If you don't like reading the question and understand it, you just start solving. You start solving wrong things. Now let's look at now what happens. We are saying we are finding the volume of revolution. Okay, we are finding the volume of revolution of the portion of the curve. This portion of the curve. This portion of the curve lies between. So this, remember that this portion of the curve, it lies between this portion of the curve. We want to find the portion of the curve y equal to x squared between what? Between x equal to 1 and x equal to 2. Okay. Now the question is now when x is equal to 1, then what will be your y? Our y will be equal to what? 1 squared, which will give us 1. When x is equal to 2, then your y will be equal to 2 squared, which is equal to 4. So now you have changed your limits of integration. Of differentiation. You have changed here, you have changed your limits of differentiation. So we are saying when x is equal to 1, so we are going to have 1 there. Hello? Okay, so now so this is 1 and 4. So when you rotate it, remember this is the curve. So now we rotate, instead of rotating it along the x-axis like this. Okay, so we have 1 up to 4. Now instead of us rotating it along the x-axis like this, instead we decide to rotate it with respect to the y-axis. So what we are going to have is this portion around here. So this is our portion. This is our portion. And along that side, so we have this portion, volume, that will form the volume of rotation. So we have that kind of a bucket. So when we spin it, it starts spinning. So we spin it like this, it starts rotating. So now we want to calculate the volume of rotation of this portion. Now, the issue is what function are we supposed to use? This is where now another challenging part is. So now from y equal to x squared, what will be x? This implies that x is equal to the square root of y. Okay, so here you have to change everything. You have to rewrite the entire function as a y function. So you have to write the entire function as a y function, not as an x function. Hence, the volume of rotation with respect to the y-axis, is just equal to the integral from, now we are now doing this with respect to the y-axis. This is equal to pi times the integral. Here now, the limits of integration are from 1 to 4 of x squared dx. What is x now? X is, this is just equal to pi times the integral from 1 to 4 of 1, the square root of 1, everything squared dx. Okay. Then, what do we get after simplifying? So what we are going to get is that this is just equal to pi times the integral from 1 to 4. What do we get here? We have the square of the square root of y is y dy. So we're supposed to have dy here, not dx. We're supposed to have dy here. And when we integrate that, what we're going to get is equal to pi times multiplied by y squared over 2. The limits are from 1 to 4. Using the fundamental theorem of calculus, this is just equal to okay, let me wrap this a bit. So using the when we integrate, what we're going to get is a pi times y squared over 2. The limits of integration are from 1 to 4. This is equal to pi. Then we have, by the fundamental theorem of calculus, we have 4 squared over 2 minus 1 squared over 2. This is equal to pi. 16 over 2 minus 1 over 2. So this is equal to pi 15 over 2. Okay? So which we can write as 15 over 2 pi units cubed. Okay, I think if you check from the part where we computed the volume of rotation with respect to the x-axis, I left pi. Okay, I left pi. In our solution, if you check, I left the pi. So supposed to be 31 over 5 pi units cubed. Okay, please, let's have questions before I proceed to the next part. Can we have questions before I proceed to the next part? Can we type some questions that you have that you want to ask me from what we've done in this afternoon before I proceed to the next part? Okay, these questions for me, no one is. Okay, how did you manipulate the x into y, sir? Okay, can I wrap the board now so that I can start answering your questions? So basically, how did I manipulate? Look, what you have is y is equal to what? X squared, isn't it? If I ask you to solve for y, if I ask you to solve for y in this equation, you are going to say, okay, in short, you have x squared is equal to y. What will be x? This means x is equal to what? The square root of y. I hope I've answered your question, Ms. Onda, Wilfred. When finding its integral, sir, please. No, we've not answered. Okay, yes. So this is how you do it. Okay, it's done. Next question. Okay, if there are no questions, let me do the last part of today's session. I think for this other part we'll discuss later. Let's look at the last part of this session, which we look at now. You remember here, under the first examples, the two examples that I've given you, is a situation where this solid of revolution has been done whether with respect to the x-axis or with respect to the y-axis. Now here you are only a situation which involves one curve, okay, which involves the graph of one curve. Now, if what happens then, if we have two curves, so we have solid of revolution created by, so the next one is solid of revolution, solid of revolution, revolution created by uh, created by two curves, by a region created by a region between two curves. So we have this solid of revolution created by the region between two curves. Okay. So solid of revolution created between two curves. Okay. So let's look at a situation now where we have this solid of revolution that has been created by two curves. How can we handle if we have such a situation? The question is, how can we handle it? Okay, how can we solve it? Okay, so let us consider, the region below. Consider um, the region, um, this region between, consider the region between two curves, y1, which is equal to f of x and y2, which is equal to g of x. Now, so from x is equal to a to x equal to b. Okay, let me sketch this region so that we are able to see it. So we have this region. We have this region. So the first thing is maybe we have a curve like that. Okay. So we have this curve, and then we have another curve. So then we are saying this curve is y1. So the first curve is y1, which is equal to f of x. The second curve is y2, which is equal to f of x. And these two curves meet at the same point where x is equal to b. And they also meet at this point where x is equal to a. Then now, we want to understand the volume of revolution of this region now, which is bounded by these two curves from the point A to the point B. So this is what now we want to calculate the volume of revolution of that region. So if you have such two curves which meet in this scenario, sorry, so we have considered this curve. So if this is the situation, then what we are going to say is that then the volume of revolution, which is equal to v. So the volume of revolution, which is equal to v, this is equal to pi. So now you look at the function y is equal to f of x is greater than the function y2. Sorry, it's supposed to be y2, which is equal to g of x. So it's greater than the function y2, which is equal to g of x. So those ideas that were applying when we looked at the situation where we have when we are being asked to find the area of this shaded region, the same concept will be applied on this one. Okay, so the volume of revolution of that region, so the volume of revolution of this region is just equal to pi multiplied by the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Oh, sorry, it's supposed to be minus pi. So when you simplify this, what you're going to get is when you do the manipulation, when you do the algebraic addition, what you're going to get is just this simplest form. We are going to get which is just equal to pi times the integral from a to b of f of x minus g of x dx here, provided um, provided you are doing the rotation along the x-axis. You can also do this rotation along the same principle can also be applied. This is so the volume of rotation is 1 with respect to the x-axis. You have that. So with respect to the x-axis, this will be our formula. And also similarly, if you want to compute this volume of rotation with respect to the y-axis, then you're going to have v, the volume with respect to the y-axis, is just equal to, again, the integral from c to d of f of y dy minus the integral from c to d of g of x dy, which of course, so you're supposed to start with pi and also pi, of which this is just equal to pi multiplied by the integral from c to d of f of y minus g of y minus g of y dy, provided uh, this f of x is greater than or equal to g of x. Here also provided this f of x is greater than or equal to g of x for all the values of x in the interval a to b, and here for all the values of y, sorry, it's supposed to be y and y, for all the variable y in the interval c to d. My marker is faint. Okay, I'll try to use another one. All right, so let's look at then an example, and this is example number now. I need to inform you that this example was done twice, so I'll only do the first part, which is where the equation has been computed with respect to the x-axis, not the other way around. So that's the one we are just going to look at. So this other one, maybe I'll let you have time to do it at your own specific time. Okay, maybe, okay, someone is saying the marker is faint. I don't know, maybe I should use a different marker. Let me just look for a very tangible marker that we can use for today. Okay, I'm back, but it's like my markers. Okay, someone is saying I should use. Okay, why can't we just end here because most of my markers are very faint. What I'll do is I'll I'll type some more notes and some more examples that involves this kind of integration, and then I'll send them to you as a group, because if I explain this question, it will be very challenging for you. But either way, I can explain it. Let me try to use the same markers and then see what we can do. Okay, now, all right, so we have example number 18. So this example says, it states that the figure shown below, so we have a figure which is being sketched there. So this is so this is example number 18. Um, Example 18. So we have a figure that is already sketched for you. The only thing that you need to do is just answer the question. So this figure, we are saying the figure below shows the part of AB of the curve y squared. So we have a curve y squared, which is called x plus 2, sorry, x minus 2, and where B is a point. So maybe let me sketch it. So we have this curve which starts like that and it goes like that. Then we have a point A here, and here we have a point C, and then we have a point B here. We have a point B, which they are saying this point is equal to, we have 1 there, this point is equal to 3, 1. So this means what we have this side is a 1, and this point is 3. Now, so that's what this question, all of you have, you already have this question. Then the question continues to say, where B is the point 3, 1, CD. So CD, so this point is D. This point D is 3, 0. They are saying CD is the tangent to the curve. CD is the tangent to the curve at a point B. I think the question is not okay. CD is the tangent to the curve at a point. So we have CD, which is the tangent to the curve at a point B, and to the curve at a point B with gradient 1 over 2. So the gradient of that tangent to the curve is, so gradient of CD is equal to 1 over 2. The curve meets the x-axis at A. So yes. Okay, so now what we are having, this is the situation. Maybe let me resketch it. So we have this curve. We have this curve. Okay. And then we have a straight line. So we have this straight line from C to B. So I think this one is supposed to be CB. CB is a tangent. So a tangent is a tangent. So we have a straight line from B to C. So we have this curve. Okay, so we have this curve that meets the x-axis at A, and then the line CB, sorry, is a tangent to the curve. The line CB is a tangent to the curve, and it meets at B, at point B. And the gradient of this tangent, which is M, is 1/2. That's what they are saying. Now, someone is saying only to the right. Okay, let me try to use the right part. Now, the questions starts. So the first question is, they are saying, 1, find the equation of CB. 2, the coordinates of C. So we need to find the equation of this line CB. 2, we need to find the coordinates of C. Then 3, the volume swept out by the shaded region when revolved round the x-axis. So now we need to find the volume which is swept out by the shaded region. The shaded region is this region. When it is rotated, you rotate it like this. When we rotate it round like this, now the volume that it is going to swim out when this is rotated with respect to the x-axis. Okay, so the secret here is, if we don't know C, D is giving us the x coordinate being 3, but we have to find the coordinates of C, because when we start, this is the axis of rotation. This is the axis of rotation. So when we rotate, it will start rotating like that. Okay? So now that's the volume that we are looking for. Now, the first one, it's about the equation of CB. Since CB is a straight line, CB is a tangent. A tangent to a curve is a straight line. CB is a straight line. Its equation, uh, its equation is given by the formula y equal to mx plus c, where c is the point where it will meet the y-axis, and m is the gradient. M is the gradient. C is the point when it will meet the x-axis. And thus, and this gives y minus 1. This is going to, which is equal to 1/2 times x minus 3. Y minus 1 is equal to half x minus 3. And this is going to reduce to y is equal to x minus 1/2, or rather you can also put it in this form to say we are going to have, this implies 2y is equal to x minus 1. Okay? So then, at the end of it all, because when you simplify this, you have 2 here, then you will put it aside to be -1. This is just the same as y equal to x minus 1 over 2. That is the first one. The second one says find the coordinates of the point C. So if you look at the point C is along the x-axis. C lies on the x-axis. As such, along this axis, the y-ordinate is equal to 0. Along this axis, the y-ordinate is equal to 0. So when the y-ordinate is equal to 0, you substitute it into this equation of the straight line. Hence, your x will be equal to 1. And the point will be as such. And so our point C will be 1, 0. Okay. Now, what's next? The next step is we are supposed to find the volume of revolution. We are supposed to find now the volume of revolution. Sorry, I've deleted the curve, but I could have shown you how this curve is supposed to do. Now, number 3, the volume of revolution is equal to, remember we have two equations. Before maybe I write the volume of revolution. We have two equations. The first equation is y squared is equal to what? Our first equation was it y squared or y? It's supposed to be, yeah. Y squared was equal to x minus 2. Okay, basically this means the first equation was y is equal to the square root of x minus 2. And the second equation, so this shaded region is bounded by this curve and the straight line y equal to x minus 1 over 2. Now, if you check the curve, the straight line y equal to x minus 1 over 2 was on the left hand side of the shaded region. The curve, or rather, it was on, let me just say it was on top, because if you look at how we sketched that region, maybe let me sketch it so that you could see a bigger picture. Let me just sketch it. So we had something like this, a straight line, which meets at C. Then we have 1, 0. Then we have a curve. We have this curve, which means at A. Then we have okay. So this straight line is y equal to x minus 2 or x minus 1 over 2. Okay. Then this curve we are seeing is equal to y equal to the square root of x minus 1, because it was x squared is equal to x minus 1. Now, this point here, point B, this point here, which was point D, was equal to 3, 0, and this point B was equal to 3, 1. So now, if you look at this region, you will now want to rotate this region. So if you look at these two regions, we are going to rotate with respect to the x-axis. Now, the question is, what is point A? The issue is we have to find point A. what is point A? So to get point A, you need to find when this curve will cross the y-axis. I mean, when will this curve y equal to the square root of x minus 1 will cross the x-axis? At what point will this curve going to touch the x-axis? This is the point A. So at point A, so when you equate the square root of x minus 1 equal to 0, you discover that your x is going to be 1. So this point is sorry, we have a 2 here. So this point will be 2, comma 0. Yeah, this equation is in the question. It is y squared is equal to x minus 2, which is giving us this curve. Then this straight line has been found after we computed. So now we are now want to find the area of rotation of this region. So what you're supposed to do, you need now to separate these two. First, you compute the area of rotation produced by the curve AB. Then you compute the area of revolution produced by the curve, by the straight line. The first thing is you now separate this. So we start by finding volume. So volume produced by, so the volume produced by AB, the curve AB. Okay, so we are going to start with the volume produced by the curve AB. So we'll start with the volume which is produced by the curve AB. This is equal to the integral. Now, if you look at the curve AB, this curve AB, the curve AB. So, and this curve is equal to what? Y is equal to the square root of 2. So this is equal to, now, if you look at this curve, the x-coordinate at A is 2, the x-coordinate at B is 3. So it will be from 2 to 3 of y squared d x. This is the formula. So this is equal to, but y squared is equal to the square root of 2. So this will give us the integral from 2 to 3 of x minus 2 dx. When we integrate this, what we're going to get is x squared over 2 minus 2x from 3, or from running from 2 to 3. Please, the other parts for computing, every one of us knows how to handle this one. Oh, sorry. We are supposed to have pi. Don't forget, please, this is also the mistake a lot of people make when they are computing the area, the volume. They forget about the pi. So when we use the fundamental theorem of calculus, this is just equal to pi multiplied by 3 squared over 2 minus 2 times 3 minus, okay, so we have 2 squared over 2 minus 2 times 2. Okay, so we have that. When you simplify this, you should be able to get an answer pi over 2 units cubed. Next, we again compute. Now, we first started by computing the area, the volume of revolution which is produced by the curve AB. The next thing is, because when you rotate this line will be rotating this curve will be rotating. So everything will be rotating in that form. So once you just rotate this, everything will be rotating. This line will be rotating, this part will be rotating. Now we want to calculate the area which is swept by this region. All right, now next we look at number 2, volume. Volume produced by CB. Volume produced by the straight line CB is equal to the integral. Now, if you look at from C to B, the x-coordinate of point C is 1, the x-coordinate of point B is 3, isn't it? The x-coordinate of point C is 1, the x-coordinate of point B is 3. So what I'm supposed to have is from 1 to 3 of x. Oh, let me check the function. So we have from 1 to 3, our function was x minus 1 over 2. Oh, first we start with, it was y squared dx, okay, of which this is equal to the integral from 1 to 3 of x minus 3 or minus 1 over 2 everything squared dx. So when we expand this, sorry for that, I'm forgetting the pi and here also pi. When we expand this and simplify, we're going to have pi. Now 2 squared is 4, that will go out. Then we are just going to remain with a squared minus 2x plus 1 dx from 1 to 3, and we are going to have pi over 4. Then we are going to have x power 3 over 3 minus x squared plus x. The limit of integration is from 1 to 3. When we apply the fundamental theorem of calculus, what we are going to get is, so when we apply the fundamental theorem of calculus, what we are going to get, which will give us 2 pi over 3. Now the question is, are we done? No, we are not yet done. What we have found is the volume of revolution which is produced by AB and also the volume of revolution which is produced by CB. Then now, after finding these two, then now you need to find the volume of revolution of that region which is bounded by the curve and that straight line. Okay, so this is now our next piece. Hence, hence the required volume of rotation is, so at the end of it all, we have the required volume of rotation is, which is V, is equal to, now we are going to have the 2 pi over 3 minus the pi over 2, which will give us pi over 6 units cubed. Okay, here we're supposed to have units cubed. All right, so this means you have calculated your volume of revolution of that region which is bounded by that straight line and also by the curve y equal to um, um, uh, the square root of x minus 2. Hence, this will be the end of our class. Um, so what I would love you to do is to go through, like I mentioned, on Monday, we are having a test. It will start at 8 hours and end at 12 hours. So those who be doing engineering, mathematics, all the courses, uh, biochemistry, molecular biology, those who be doing biology, chemistry, physics, maths. Then we also have those who be doing engineering, mathematics. Any person who will be doing biology and chemistry, you are going to be applying these things. Okay. So right now you could feel, where am I going to apply these things? But if I give you some questions on applications of integration, you'll be very surprised, which are in details. So now, so this is the end of the class. As such, I would wish you to say all the best with the test on Monday. But there are other notes which are remaining. I'll send them before by evening, which involves applications of differentiation. We'll see. Maybe after you write your test on Monday, then we are going to revise. Or, I mean, on Tuesday, we are going to revise some questions from the past papers that I've seen. I'll send the past paper on Moodle for last year and the other academic years, uh, so that you go through on things to do with differentiation and integration. Then we are going to see what we're going to do on Tuesday. We are going to revise some papers. At least I'm done. For applications of differentiation, as we'll be revising on Tuesday, we'll also be going through those notes on applications of differentiation. So thank you very much for your time. Enjoy your weekend.